बाहेक अरू बेला पढिनु जाँचमा बाहेक अरू बेला पढिनु अनि त्यही छ
Is this you? Do you hear me well?
Yeah, we're here.
Okay, okay. Thank you.
Thanks.
Okay, thank you very much for coming.
Dr.
Yes?
Dr. Kilin, could you please make D2L accessible for us as well so that we don't have to like ask you for every notes and everything, like we might like
I was trying to do it, but in order to add out of campus people to D2L, I need something like your student ID, some
Sure.
detailed information.
Okay, okay, we can provide that. You need our ID number?
ID number and maybe something like address or phone number because they want to have a database.
Okay, okay, we'll
send me an email and I give you the list what is required.
Sure. Thank you.
Well, thank you for coming, and we'll try to continue what we are doing here. So, last lecture and this lecture are mostly challenging and difficult. They have a biggest, largest portion of math in it. The rest of lectures should be relatively easier starting from next week, and they will have more substantial practical component. So I do not have handouts today. Maybe we'll do it next time. And I have designed a couple of other homeworks, but I will try to distribute them either today or maybe next week. And it is something really easy that will not make a lot of time or will not take a lot of your time. So we still are trying to make presentations in a week from now, next Thursday. So instead of me, volunteers will come up to the stand and make little short presentations. And I have several people who already volunteered. We'll probably discuss it at the end of the session. Last Tuesday night, some of us went to the computer lab, and our major advance there that we have practiced to use the Gauss view software, which allows to compose, build atomic models, and it is important practical skill to go further. So we will try to practice the skill a little bit more on the coming Tuesday night, and we will also try to cover two other little pieces of software for visualization and for converting XRD data into atomic models that can be calculated by other software. So where we are now, what is our goal? what we are doing. So we are trying to put quantitative accounting of properties of materials and molecules. We are building atomic models by setting up positions of atoms, number of electrons, and since we do want to treat them on the precise quantum level, we are building energy operators and building Schrödinger equation for these molecules, which are set of ions and electrons. And the challenge that we are trying to address for several lectures is there a way to treat ions and electrons separately? Is there, because there are so many of those, and treating all of them together is too complicated. And if we get any success on this road, it will be really beneficial for the rest of the class. And there are good expectations to complete this task today. So in the last lecture, we carefully viewed the molecular Schrödinger equation, where the energy operator contains all possible terms of interacting electrons to electrons, ions to ions, electrons to ions. And now we are trying to split this group of contributions to energy and put each of them into different equations. So it is in a basic what we are trying to do. And on this road, I'm going to recall the last slide from last theory slide from the lecture, which was corrupt, and I don't know. On the home computer, it looks nice, but here it is a little bit shifting. So we are observing that after treating all electron terms as one equation, they do set a basis for further treatment. Electronic wave functions, they are good basis. And then we are trying to compose an equation for expansion coefficients, which also treat the properties of ions. And in this equation, we identified 4 terms, and only the first of them is challenging. The rest was straightforward. There were no quantum properties in the second, third, and fourth term. So no substantial quantum properties. Just trivial. And the first term, which corresponds to energy of ionic motion on the quantum level of description, is something that provides a little challenge. And we are going to focus carefully on the term that describes contribution to the energy from motion of ions on the quantum level, and see if we can separate it on some pieces. Are those all pieces of significant importance, or we can neglect something? And the expectation, the wish, the goal is that we will find some terms which are small, and by neglecting them, we will get 2 sets of equations, one for electrons and one for the ion. And they are much more easier to solve. So in the first term, let me bring it up. So a couple of minutes of labor to type it in instead of writing right now. So the first term, which is contribution to the energy of a molecule appearing from motion of ions on the quantum language, we have the following terms. Just focus on them. So those phi functions, those are basis functions for electron. And we are going to eliminate them due to a property of orthogonalization. So we are multiplying by another function on the other side, and we expect to eliminate any electronic wave functions, to go from functions to numbers, to matrix element. Then we do have this chi functions which have a twofold importance. So these chi functions, on the one hand, they are expansion coefficients telling which proportion of each electronic state contribute to the whole state of a molecule. So on one side, they are weight coefficients for electronic state. On the other side, we have already discussed, or we will see in the future, those functions at the same time they work as wave functions of nuclei, of ions. And formally, the equation that we are solving right now is Schrödinger equation for wave functions that depend on position of nuclei, nuclear wave function. Ionic wave function. Okay, so there are some summations, summation over all electronic state, summation over all ions. And here we do have a operator of kinetic energy in quantum form. So we know that kinetic energy is proportional to square of velocity, or more convenient, to the square of momentum, right? So E square over mass. And in quantum case, we replace the momentum operator to derivative over position. And because of square here, we have a square here. So the second derivative in respect to position of ion. Okay, so the announced challenge is not very big. We just need to recall the beginning of calculus and take second derivative of product of two functions. Because ionic part explicitly depends on position of ions, and electronic parts also parametrically depends on where ions are. Okay. So we do have this I, and we are going to take the second derivative. Well, to save number of symbols on the board, we can abbreviate the derivative as just apostrophe sign. So 2 primes means second derivative. And then we can apply, take first derivative to both of functions, and then second. Anyone wants to help me and teach me how to take derivatives of product? Okay. And then we need to take derivative once again, right? So from this term, we are applying same rule of getting more terms. So we get I 2 primes A. And from here, get I prime without prime, phi is second derivative. Okay, So we are done the only non-trivial part. The rest is just accounting of terms and analyzing what do they mean. So we were thinking that we do have only one term for kinetic energy, but now we observe that there are 4 of them. And maybe some of them are more important, some of them are less important. And we are going to think, discuss, and probably neglect some of them. So let me go further. Probably I have already typed this thing in computerized form. Yeah, we take the second derivative. We have 2 terms, and then we have 4 terms. And here I was not lazy and just put these EDR symbols. So we have second derivative in respect to ionic wave function. Right? And if we do have ionic wave function, or wave function of some particle, and second derivative in respect to main variable, this will be a traditional definition of kinetic energy. So this last term, when we apply derivatives only to this chi function, to ionic part, it is leading term. It is most important term that one cannot neglect. It is often referred as pure kinetic energy. Pure ionic kinetic energy. And the rest of the terms have some mix. Although we are speaking about kinetic energy of ions, it also depends on some properties of electronic wave functions. We have this derivative, and here we do have a second derivative. And by the way, these 2 terms are look the same, so we can just plug it here. So we do have a pure term for kinetic energy, and we have some terms that provide some unknown, strange, crazy mixing between behavior of electrons and ions. And it is the feature, it is a term that for some applications it is very interesting, but for most applications it is just a bothering factor that complicates a lot of calculations. And if possible, if it is not important, one always wants to erase it with some good motivation. When we can erase it? Well, if we predominantly know from our common sense, from some experimental observations, that motion of ions change electronic states, or changing electronic states affect motion of ions, then we cannot neglect it. So if we know for sure that electrons affect ions, or ions affect electrons, then we need this mix. And let's discuss which examples we can think about. So probably if the material, if the molecule is heated to the really high temperature, if it is like plasma or very hot vapor where one sees the bond break information, probably reactions where one applies strong laser field and electronic states are changing upon irradiating the molecule. One has different types of ionic motion, and they are connected with changing electronic state. There one needs this specific terms. Probably some reactions like electron transfer. When for reactant and product one has different potential energy surfaces, and while changing electronic state, one also has a change of forces that do affect ion. So in all those examples, one cannot forget about those terms. Plasma, reactions, maybe fragmentations. Strong laser field. Electron transfer. So those are examples when it is when we cannot neglect them. In most standard situations, when we have room temperature or even 0 Kelvin cold molecules, no one disturbs them. They take their most optimal geometries. One disturbs them with very weak light just to probe their spectra. Then those terms are not necessary, or they, even if they are present, they are substantially smaller than the other terms, and it is very often very frequent approach to neglect them. Okay, just returning to same boring derivatives. So when we do have second derivative of ionic part, it is a pure kinetic energy, and we keep it. We always keep it. When we have a mixing terms that has derivative to ionic part times derivative to electronic part, or if it is a second derivative to ionic part, we seek any opportunity to forget about them, provide any motivation that they're not important. And it is what was done by this persons, Born and Oppenheimer, whose portraits and short biographies I was trying to include in one of the previous lectures. Born and Oppenheimer want to erase these terms. Okay. So, although for the remaining 20 or whatever, 22 lectures, we are going to neglect it whenever is possible, we want to be very rigorous, precise, and have a definition of this term and correct language to describe it. So those terms that are typically neglected in Born-Oppenheimer approximation are referred to as non-adiabatic coupling. And from common sense, the adiabatic means something changing slowly, there are no abrupt jumps, and non-adiabatic means that something is happening. Like electronic states are jumping from one to each other. And here, I'm not showing anything new. It is just repetition from the previous slide. So here we have the ionic part, and here we have an electronic. And there one term where we apply derivatives to both ionic wave function and electronic wave function, and the term where we apply derivative to electronic wave function only. And excuse my own laziness, I was replacing the integration e pi star I a dr into the notation I e pi a, which is referred to as Dirac notation. there are several integrations, if there are too many variables, one can often use this notation for convoluting wave function. This part, you probably know it, but I'll repeat. This part is referred to as bra, and this part referred to as cat. And Dirac designed them because he took the word bracket and just split it onto two parts. Okay. So in our practical implementation of molecular Schrödinger equation, this non-adiabatic coupling enters this equation under the summation sign. And under this summation sign, what it does, it connects electronic states with different indices. So we should keep in mind the twofold importance of this chi function. This I is on one side, it is weight for electrons, and on other side, it is ionic wave function. Ionic wave function. If you think about it as weight for electrons, we see that this summation, there should be summation over 1 in A. Summation over A, A there deletes, and then the result will depend on B. So it mixes different electronic states in the final equation to describe the situation when electronic states are not independent from each other, and depending on ionic motion, electron can jump from one state to another one. So probably for the rest of the course, we are not going to touch those highly exotic situations, but for later, for bigger vision of all possibilities, and for our future research projects, it's better if we keep the language and understanding what may happen if we disturb system in a substantial way. This is non-adiabatic cup. Here we use the Greek letter theta. Theta. So let's recall our equation that we were playing with on the previous lecture, or with our terms, numbered terms I, and term number 4. So those three last terms were trivial, and we agreed that nothing interesting about it. And today we were playing with the first term, with kinetic energy of ions that does reflect quantum property. And by making a closer look on it, we have identified that this quantum form of ionic kinetic energy has two contributions. One of them is pure kinetic energy that corresponds to what one was expecting to see here, just applying momentum operator directly, explicitly to wave function of nucleus. And there is a second term which provides mixing between electrons, ions, transitions between electronic states. And in real life, when there is no exotic interactions, for like 99% of situations, for relaxed ground models, one can neglect it. So we look on this equation mathematically, we see that all other terms do have a delta function that appears from diagonalization, which means that delta function and summation dilute each other. And instead of them, we replace the index A to index B. So we substantially simplify the equation. We remove the sum term everywhere, which will be very good. Also, before we erase this mixing, all our treatment was precise. So the first approximation in our course is appearing right now. So we can celebrate first approximation. Before, all equations were exact. Therefore, no one can find solution. So it was precise, and starting from this slide, we will do approximate treatment. Okay, so we have deleted the summation, and now we erased the non-adiabatic term. Electrons and nuclei become decoupled. And then, without this summation, we do have 4 terms. Pure kinetic energy, Coulomb interaction of ions to ions, just Coulomb repulsion, because ions have positive charges, and when one tries to bring them too close together, they start to repel. And there is an interesting term, which in some way there is a still connection between electrons and ions, but it is a easy connection. It is a healthy connection that doesn't present too much mathematical problem. So please highlight it once again. This term means that depending on state of electronic system, whether it is ground state or maybe someone has excited it, one does have a little contribution, a little additional contribution to the potential energy that affects the motion of nuclei. So this, after we go from row by row, listing of terms into just have all terms together, we see that it looks very much like standard time independent Schrödinger equation. It is equation for nuclear wave function with unknown wave function and unknown eigenenergy. And typically, it should be expected to have 2 contributions to the energy, kinetic and potential. And in the potential part, we do have 2 terms. One is well expected, standard interacting of ions to each other. And another is contribution from electronic energy. Contribution electronic energy. And we shouldn't worry here. It is a healthy contribution. It is not challenging in mathematical sense. Okay, So since we do have a little bit different potentials for we have different for ionic motion depending on electronic state. We draw the dependence of the potential energy on ions, and typically if we are at ground state, at low temperature, no perturbations, all ions want to stay at their optimal position, at their equilibrium positions. Equilibrium. But we should understand that for ground state, it will be this V plus E with B equals 0. So for ground electronic state. As soon as one changes the electronic state of the system, the potential that ions are experiencing may differ. So it may change the equilibrium position, it may change the curvature, and it may become even something strange, exotic, non-harmonic. B is the index of electronic state. Yes, potential of ions interacting to each other. B equals 1. B equals 2. So the potential affecting ionic motion does depend on electronic state. So instead of one potential, we have as many potentials as many electronic states we have. And since it is not one ionic degrees of freedom, there are typically like 20, 200, 2000, 10,000, depending on the size of your material. This is the multi-dimensional potential. So it is not a line, but it is a surface. And therefore, one uses the term potential energy surface. And typically, when one speaks about those potential energy surfaces, one keeps in mind that they are different for different electronic states. It is, well, I just draw arbitrary dependence. Typically, potential energy surfaces have a minimum and behave parabolically near it. But in some exotic cases, it may have 2 minima, or maybe 3 minima, maybe 4, I don't know. And they may have saddle point, like different inflection points. It is a big sub-branch of science to explore those surfaces. Let me just write down the term. So those are potential energy surfaces. Yes, yes. Here, I'm trying to be a little bit more rigorous than is probably necessary. And instead of word atoms, I pronounce ions. Because before someone solved these equations, we do not know whether a specific atom will be ionized or not ionized, because electron there is no label on electron that electron belongs to specific atom. It may go from one to another. And we are talking about nuclei, the ions, and their position in space. And as we solve all equations related to the molecule, we may find that electrons are forming clouds around this ion, or maybe they do not. So we are trying to speak completely separately about electrons and ions. Position of atom, yes. Yes. This illustration probably will correspond only to diatomic. When we have one dimension, yes. Also, potential can be dissociative, right? Another possibility is something like this. If you create some electronic states, it may promote the breaking of the bond. Okay. If you have time and steam, at some point we need to cast this equation in time-dependent form, because ions sometimes move. We want to see what happens as time passes by. And also, in very many cases, the quantum properties of ions are not so important. If there are no excited states, if there is equilibrium position for each electronic state doesn't displace as much. If we are not interested in the femtosecond or attosecond regime, then there is another good approximation that we are looking forward to apply maybe on Tuesday, to go from quantum limit, from quantum treatment of ions back to the classical limit. So we should look onto typical way how ionic wave function look like, and see if one can consider it not as a distribution in space, but just as a point charge. But we are trying to do all the steps carefully and provide at least some verbal analysis and background for doing it. Okay, so if it is a time-dependent form, we just do standard time-dependent Schrödinger equation with Hamiltonian wave function and time derivative. And what we are going, probably it will be too much information to focus on it right now, but this nuclear wave function, depending on position and time, could be, in many cases, considered, at least for ground state, for some state. There is an approximation of considering it as a traveling Gaussian wave packet. So as time passes by, the ions have a little probability to be in one location in one position of space, in another position of space, and this distribution changes in time. But in many cases, it is enough just to specify the center of this distribution, and the center often moves according to classical Newtonian mechanics. I hope to touch this subject in more details on Tuesday. Nuclear wave function. Is maximum. It is a distribution. And it is often enough to track the center, the center of this distribution. Okay. Let me summarize what we have completed today. So we are trying to formulate a quantitative approach to describe any quantum properties of molecules, of material. We have formulated the molecular Schrödinger equation, which depends where the solution should be a distribution depending on all positions of all electrons and all ions. And without any approximations, we assumed that one can try to look for such solution as a product of electronic wave functions with some coefficients. Any question? So, in case we neglect specific term in kinetic energy, which is referred to as non-adiabatic coupling, we get a substantial benefit. We remove the summation, so we have just product IA times IA. So we should be specific that our electronic system is only in one state, not in the superposition. And then we do have two sets of equations. One set of equations is to find all possible electronic states. And another equation is to find all ionic states or quantum dynamics of ionic states. There are opportunities to solve them independently. And it is what computational chemistry, well, not computational chemistry is not a person, but what software tools developed in the area of computational chemistry are doing. So the 80 or maybe 90% of all computational chemistry efforts are just solving for electronic part and making some simple assumptions or approximately solving the nuclear part. But this Born-Oppenheimer separation did a great job for us. So we reduced the amount of variables because this function is not possible to solve at all. Well, in a practical sense. There is no formal restrictions to solve, but it will request really too many of numerical or human resources. That is not on time scale of our life. Okay, yes, here it is what we already discussed, the definition of potential energy surface, which depends on electronic state and on eigenstate of electronic subsystem. Should I keep the slide there? Someone was taking that. And now we can just this is already done. Potential energy surfaces as an example. And here is the list of what we have completed and what we plan to do when we meet next time. So we did an analysis of kinetic energy of ions at quantum level, and we practiced a little bit of calculus of taking derivative and found that there are terms which are more important and there are terms which are possible to neglect. So pure kinetic energy should be kept and non-adiabatic can be removed. Then we have enriched our arsenal of terms and concepts that we possess with the definition of non-adiabatic couplings, and we have an idea in which situation might be necessary to treat them. And we understand that it is not always. For many systems, many situations, it is not necessary. And we got a substantial step forward. We have a set of equations for electrons and ions that we are going to address. We are going to, well, we are not going to solve anything. We are going to set up tasks for computer to solve those equations. And when we meet on Tuesday, we will talk a little bit more about classic limit of ionic motion. Then we do a transition. We describe it as equations of motion for these point charges, and we will formally define one of the important tasks that computational software is doing for us: the geometry optimization. When we draw some initial structure, which can be right or wrong, and then we set up a task for software to check whether this geometry is correct based on all equations that we put into the software. And in many cases, the geometry computed according to these rules is in a very good correspondence with what is observed in nature. And the additional benefit that one can look on some exotic compounds that are never been sensitized. So with this, I'm finishing the theory part. And if you like, we can briefly discuss our plans for our meeting in a week from now. Are there any questions for this theory material? Probably not. Okay. I'll try to design a homework that will sound like prepare a question for the next lecture. So when we meet next Thursday, it would be great if some of you volunteer and share your own experience that you did learn in the basements of art and science building, of operating the Gauss View software, of basic Linux commands, and hopefully we will cover these two last things, also converting between different formats. And I do have 3 emails with volunteers to this subject, and this subject. So there are still plenty of opportunities. And the presentations, which should be really short, maybe 3-4 minutes, will provide a substantial extra credit. For example, if you have any problems with other components, not doing homeworks, but being excellent at these presentations, it will outweigh all other things. I encourage you to volunteer and present. For the rest of the semester, I plan to offer to the whole group the 4 sessions of presentations. So the first one should be just basic skills that we are going to do in a week from now. Then there will be very simple computation of basic properties using Gaussian software. Then there will be basic properties with VASP software. And the fourth one, which is optional, but last year it was the most interesting and most pleasant part for all the group. There will be presentation of independent research project. And approximately they are spaced as 1 session per month. So what we're doing next time, it will be for January, February, March. It is a little outlook what we may expect in the future. For the subjects that we are doing in the lab, there were some questions from SDSU part on the very first thing, how to get an access to Cygwin software.
Yeah.
And it is best thing, of course, is to sit nearby, but let me verbally tell what it is.
Okay.
So if you are trying to install it at your home computer, at your laptop, there are several steps: downloading from outside source, and then before you click the install button for the last time, at the end of this installation process, there appear pop-up, or not pop-up, there appear panel or space to type something similar like in your navigation panel. And there you can write which parts of this Cygwin software package you want to install on your computer. And as I recall, you had problems with running graphical applications, with doing this X Windows, X term. Yeah. So please try to type in those keywords in the navigation panel. Cygwin navigation for installation. So there will be a panel And before proceeding, you can try to type there several substantial components, SSH. So it is just commands that need to be there. X, X. And then proceed. Then you hit the button install. So then your software piece will be much more powerful. And by definition, they may skip those components.
We'll try.
Okay, I think we are done for today. If you have any questions, suggestions, please address them, but otherwise class is dismissed.
Thank you.
Thank you.
एक घंटा वैसे भी